And they are getting ready.
Okay. Don't go back to the logo. Will you? Do you want to tell me when to take the slides? Do you want your slides up right now?
Oh yeah, the slides can be.
Okay. Okay. Are you getting a second computer in?
Yes. So we'll switch the HDMI.
Do you want this computer up there too?
Yeah.
You want to see both of them?
Yeah, we will switch the
Okay. Yeah, no, we'll switch them. You have to tell us which one. Where's my HDMI? Okay, where's your HDMI? So you say slide 1, slide 2, just to say. What deck do you want to start out on? This one or the other deck?
we will start on
You start there.
We're going to start off.
Sorry. Sorry guys, please wait up for a few seconds. Our assistant is kind of unhappy after cutting rain, so yeah. Set? Yep. So hello guys, yeah, thanks for the waiting. So we're the PhD student from RPI. I'm Shinan, and this is my colleague Jinghan. Yeah, we're representing RPI to attend this SHM in Action show, and also our project is funded by the DARPA. So our objective of this project is to want to show like the sensing capability for the embedded smart structures. So I think Jinghan will have a very brief introduction about the manufacturing process.
Hi everyone, welcome to our speaking. And we know our novelty is to try to build a fully embodied smart structure by using wide arc additive manufacturing. So nobody has been done to actually make a fully sensor embodied structure by using this additive manufacturing technology. And luckily in RPI, we have a very fancy multi-sensor fusion WAM test bed. By using this test bed, we can build a very high quality, which means less porosity and something part. And we just fully embed the sensor inside this WAM structure. And we have the capacity to embed multiple sensors inside. The maximum capacity for a very small beam can reach to 14 sensors. And we do have the RTDs and strain gauges, as well as the PZT sensor embedded for different sensing tasks. And this is the picture of how our smart beam looks like, very clean.
Yeah, thanks for his introduction. So our design will be two layers. One layer is above the neutral axis, and the other layer at the bottom, lower the neutral axis, which have the capacity to capture both compression and tension. And we also have RTD inside. And here now we want to switch to our the other monitor to have some real-time demonstration. So it's already switched. You can see here. So we have one strain gauge. I noted here. Strain gauge 1, it's above the neutral axis, and the other 2 is below the neutral axis. So now if I press this beam, so you can see this green one, it's obviously under tension, and the other 2 is under compression, which means the sensor embedded in the metal is totally functional. And if I do reverse, you can see exactly opposite. So I think it's a provement that our strain gauge have the totally functional ability after like so many WAM and thermal process. And next, we want to show the functional ability of our RTD embedded in. So here, this is the RTD we have. So I need to change it to like a longer window time. And we'll use solder gun here. So Jinghan will help me with hitting a random place of the beam, so you can have a look. So you can obviously see the temperature going on and going on. Yeah. Yeah. Can we switch back to the laptop? Yeah. Yeah. So, but anyway, we just captured the point data from this whole beam. So for the real application, we cannot come up with, we try to reconstruct the whole fields, the continuous fields measurement. This is the reason why we introduced physical informed neural network. So I have a brief video here. So you can see we combine the 3 experimental RTD data with the thermal equation, convection, conduction equations. We successfully reconstruct the whole thermal field using limited data and the extrapolation the resolutions. And we also have 4 thermal couples on the surface to do validation, and you can check the fitness here. So for more smart structures and for more applications, you are very welcome to our booth, like come by and communicate with us. So this is our demonstration. Thank you.
Okay, one second.
put you on the left. Do you have his video? He's on one. No audio. Whenever you're ready, just start talking.
Hi, my name is Hun Sun. I'm from KAIST in South Korea. Today, I'd like to show you a high accuracy and low cost displacement sensor. So when it comes to civil engineering applications, most of SHM systems are installed mainly for large scale structures. But if you look at United States, we have over 600,000 bridges, but less than 1% of them are actually long-span bridges. So we need monitoring systems specifically designed for small and medium-sized structures. But we see very little SHM systems for these small and medium-sized structures. Why? Because they have to be very, very cheap. Second of all, for displacement, the accuracy has to be much better. So we address these two issues by combining millimeter wave radar and the MEMS accelerometers into single sensor unit. So the size of our sensor is the size of this business case. Maybe it's a little bit thicker than this one. And then the cost is cheaper than your iPhone. Okay? And then the accuracy is better than 0.1 millimeter. And then we transmit data using wireless communication, and then we provide power using solar panel or batteries. And we don't need any additional data acquisition system whatsoever. Every computation is done inside of the sensor. So let me explain the working principle, okay? So from the sensor here, we send out radio signals. And at the fixed point, we're going to get reflections, okay? Then from the phase shift, we can get displacement. But the problem is that there are multiple waves which can produce exactly same phase shift. So this problem is called ambiguity. This is a very well-known problem. But what we do is, because we have accelerometer inside, we can also estimate a phase shift from accelerometer. And then the closest one to the phase that we got from accelerometer is a true phase. Then we can get displacement and continue. So even though I show something like this, people don't trust me. So I always have to do field testing. So we have done testing in Korea, United States, and China. So this is a list of the results that we obtained. But remember, all these structures are small and medium sizes. So you can see that the average maximum deflection is less than 1 millimeter. But still, the accuracy that we were able to achieve was less than 0.03 millimeter. And I know that still you're not going to trust me. So Foucault, can you recognize this structure? So this is the parking structure inside of the Stanford. So what we have done was we installed our sensor beneath this ramp. And then we tried to measure the displacement. So this is our sensor, and this is a very expensive laser device so that we can get reference displacement. So we drove our car over the ramp. So you can see that the maximum deflection is less than 0.2 millimeter. And then this is the error that we were able to achieve. Okay? And then this is like static deflection. And also we tested highway bridges in South Korea. And again, this is the only sensor that we install with some battery and nothing else. Okay? And then we also tested as a high-speed train is passing by. Remember, even though when we have high-speed train, the maximum deflection was less than 1.5 millimeter. Okay? Here's the last one. So the key is this one. If you look at the peak displacement, can you see how accurate it is? Okay? And I don't have time, but also we can estimate acceleration as well. Okay? So that's the end of my presentation. Thank you very much.
And our next group is N+.
You don't see it right now by chance, do you? Yes, no? Did a warning message come up about mirror? With the mirroring options, it's going to ask if you can share. Do you know where I might find that? It never popped up. Is this an Galaxy? It's a Galaxy? Oh, it's a Galaxy? I did too. It's a Galaxy. So maybe start.
Yeah, try the other one. And no, Android devices are not.
We thought it was.
I'm sorry, I thought it was an iPad.
But still.
Yeah, I'm sorry, I'm not an Android.
Here. 4 and 5.
Good day, everyone. We are Francesca Briganti and Alessio Giori from M+. We are a manufacturing company that builds structural health monitoring sensors that are applied on over 850 bridges worldwide. Today, what we would like to show you is how we actually go from our installation to the configuration of the system and the acquisition of the data, the entire process. We weren't able to connect the iPad, but I'm going to show you just live. First of all, once we have installed a structural health monitoring system like this one on a bridge, the first thing that we need to do is to configure the system. So the way we do that is by using an iPad like this one. We have a special application where basically what we do is that we build an entire configuration by just, I'm sorry if over there you cannot see, but by just scanning the QR code of the devices installed on field. Sorry, this is a little bit blurry. Okay, one moment. Okay. What happens once we have scanned is that we can see the entire configuration of our system into our iPad. This application is especially given to the people on field, and we are able to see whether they connected everything rightfully, and we are also capable of seeing pictures of what they have installed. Now, what we do is that we have a proprietary platform through which we can, we can actually see all of our systems. Let me enter into one. We can see the installed configuration and the installed sensor with their precise location. We can enter into each and every sensor and visualize real-time graphs. In this moment, this is the application connected to the real-time graph. So let me just show you. The real-time acquisition. It's the internet connection, probably, sorry. And what we can do is that we pass from the acquisition of the data to the data analytics, thanks to a specific module of the structure. What we can especially do is that we can specifically assign structural health monitoring parameters, like, for example, the rotation of a span, to a certain number of sensors that concur to that measurement. What we then can do is that we can set thresholds or alarms, and we can do that in two ways. First of all, we can do that in the engineering way or per the code. So you just enter manually the limitation that you have on that set parameter, for example, rotation. Or you can do that automatically through statistic algorithms. So, for example, you decide which statistical parameter you want to set the threshold on, and you can use specific algorithms, for example, control charts or predictive or machine learning methods. And the software automatically assigns thresholds. Then I can see how all my sensors connected to a specific SHM parameter are doing in correspondence to the thresholds. What you can also do is that you can, for example, code your own experiment and code your own algorithm if you want to see something specifically. For example, you want to compare the vertical deflection of several spans, and you can apply this model to a set of data. by applying the model to a set of data, you are capable of seeing the result and also getting a tooltip from AI, which gives you a preliminary interpretation of the data you're looking at. So this concludes my presentation. If you're interested to see actually live that we were able to connect, or to hear about this not at the speed of light, please come see us at our booth. Thank you very much.
I'd like to invite Stanford University
Which one needs the sound? This one needs sound. That one needs sound? Sorry, actually, no one needs sound. Okay, here's a connection for one. Do you have an HDMI on the other side? You need USB-C. Yeah, potentially not to connect sound because I need to play sound through this speaker. Whatever you'd like to do. No sound through here, but I want sound like to my sound. I already connected Bluetooth to my sound. Okay, this is going to go to the screen. And then do you need that to go up to the screen? Do you have an HDMI port on this computer? Yeah. Okay, this computer here is number 2. Yeah. Oh, I was supposed to go you've got to tell this computer to mirror whatever you want to mirror. The whole screen. Yes, and then click yes. Hold on. Can I test my sensor first? You want to test something? Okay, test on. Okay. Yeah, we're good to go. Where's the sound? Did it come out? No, not sound. I just like tap it to make sure it's working. Okay, I guess I'm ready. Mic number 5. Oh, I'm sorry, mic number 5. Yes.
Hello?
She wants input 1 of
Yeah. Good. Yeah. Thank you. Hi, everyone. I'm Yuyan Wu. I'm a PhD candidate from Stanford University Structures and Sensors Lab. Today, I'm going to do a demo about my research, human body weight estimation through the bed structure vibrations. So, first of all, body weight is a very important information in the emergency scenarios, because inaccurate body weight information will lead to wrong medicine dosages, which can lead to very severe results such as organ failures. And it's actually a very difficult task for the hospital emergency department to measure people's body weight, because usually these people cannot stand up. So it's very challenging to measure them with a traditional weighing scale. So we developed a novel on-bed body weight estimation system through the bed structure vibrations. Here is how it works. Imagine people are lying on the bed. We use the speaker, which is attached to the bed, to play sound to induce the bed to vibrate. And then the vibration goes through the bed and the body system to the other side, and then it is captured by a vibration sensor on the other side. When people of a different body weight is lying on the bed, the vibration pattern will be different. It's because people's body weight affects the mass of the bed body system, and thus will affect the bed vibration response. So to this end, we can infer people's body weight with the bed vibration response. And we tested this idea on a bed with 11 people, and based on our data collected, our evaluation shows that this system can reach 1.5 kg error for 11 people. The x-axis is the ground truth weight, means their actual weight, and the y-axis is our estimated weight. We can see that the estimation is very close to the one-on-one line, meaning that our system is performing well. However, like we previously thinking that we can pour a hospital bed here. However, after arguing with the organizations, we are not able to pour the hospital bed here. So unluckily, I can only show you with like the idea with this small table here. Here I will put weight on the middle of this table to simulate that is a body weight applied to the bed, and then this small desk simulates a bed. And then here we attach the speaker to one side of this table, and then two geophone vibration sensors on both sides of the table. Yeah, can I change to another screen? Okay, yeah. Okay, let's start the vibration collection. Let me first test the vibration sensor is working. Okay, it's working. It's my tapping, and yeah, this is my stamping. So now I already put some weight here, and let me play some music to excite the bad vibrations. Let me find the music. Actually, the music is written by AI. Yeah, so here these vibrations are the music-induced table vibration. You can imagine it as a music-induced bad vibrations. Yeah, this music is written by AI is because that the hospital requires us to have a soft and natural music. However, it's challenging for me to write music within the weight-sensitive frequency band because not all the music can work. We need the music to have the high energy on the certain frequency band, which can make the weight estimation system work. So we convert the frequency band information into the 1, 2, 1, 2, 3, which is they call do re mi, into the prompt. We put input to AI and let the AI give out the soft and the natural music, which is what I played. And then let's input the estimated start time of our of this music-induced vibration. We can see this part is a music-induced. It's almost starts from 35, and here I put 48. And let's go to the weight estimation. Yeah, it's calculating. And it may take some time because this laptop is very old and cheap, so and the CD is almost full, so it may take some time. Okay, we got the value here. Thank you.
Next groups come from Sweden, Royal Technical Institute of Technology.
Hello, hello, yeah. So, hello everyone. My name is Gracie. I'm from KTH, Sweden, but I'm not Swedish, as you can see. I'm from Brazil. So, just a little background about this project. I'm an electronic engineer, someone that really likes to be in the lab. And yeah, what I'm doing here is I really like to embed everything. So my PhD was about scalable hardware solutions for machine learning. And SHM was the third case study. So my first focus was just making the hardware pretty. So, and now I'm doing my postdoc with Sept, and now I'm looking more on the front end where the sensors lie. Yep. Because we have only 5 minutes and I couldn't bring my structures all the way from Sweden, it would be very challenging. Then I'm gonna show you a short video from the data acquisition phase, but I already have also the damage detection phase, but right now I will focus on the sensor part. With a scratch in the middle. And I have one transmitter in the middle and 4 receivers, one at each corner. Imagine having 16 receivers or something like that. FPGA is a field programmable gate array device. We can program it on the go during the run. These boards, analog devices they gave to us, it's PCBs dedicated for busy keys. The scratch is between receivers 1, 2, 3, and 4, so it's between 2 and 3. And then we would have the second stage, which would be the damage detection, but student that is working on keep all the electronics pretty. So right now we are 3D printing a box, a package to put everything inside, and also an interface. So hopefully next year we're gonna have a prettier system to show you. Thank you.
I'd like to invite Kisla.
No audio. Yes. Let me know when you're ready.
Right now. Okay, the color has been a little bit weird. So, hi everyone. Thanks for assisting till my last presentation. My name is Giacomo. I work for Keystone Instrument from a Swiss company. And today we show you a demo from a bridge that we have located here in US, in Rhode Island. But before this, I will say just a couple of lines. Basically, in Keystone we measure everything. I think that you're already better aware about the company. Basically, our sensor has been used for different applications, especially those one that someone before me presented as aerospace and also aviation. I'm in charge for the bridge health monitoring application. And in my view, basically, we combine two different technology, wake in motion from one side and the other side SHM. I think that you are more expert maybe than me about SHM. I will just give you a couple of lines about wake in motion. Basically, it's a linear sensor that is located in the asphalt and is able to detect basically every type of truck, cars, and monitor the traffic. Why is this important for us? Because SHM is a topic that is widely spread around the world, but unfortunately, a lot of applications are still missing the important role of the traffic. That is basically the main pain that is affecting the structural performance of the bridge. So in this application that I will show you soon, basically this bridge is located in Rhode Island, is Washington Bridge. Maybe some American expert is already aware about this critical bridge. And for this application, we installed more than 10 different different position linear sensor for wake in motion and more than 200 structural monitoring. Why? Basically, this project was very important because, as you can see in here, there are two big concerns. Basically, the west span has been gonna be demolished. So the first concern of Rhode Island DOT was to understand the vibration during the demolition phase, while in the second end, as it's very trivial to understand, basically if one span has been demolished, the traffic was moved in the remaining one. So the traffic has been increased more than 50%, passing from 4 lines to 6 lines. And now we show you some insight from the live dashboard. I hope that everything gonna work. Yeah. You can see, yes.
Is it supposed to be green?
Sorry?
It's not supposed to be green, right?
No, isn't it?
We're going to try different input real quick, okay?
Thank you. Actually, the company color is light blue, but this green is also nice. Oh, fantastic. So thanks. So as you can see here in the dashboard, sorry, but I don't have a pointer. You can see all the channels for every type for each span. Here we have 14 spans. Here it is possible to represent also the location of the sensor. We monitor it with accelerometers in a configuration that is monoaxial and biaxial. Why we don't use a triaxial? Because you are very expensive, so we prefer to reserve some channels to give a really important data and not just use, for example, the longitudinal component in some parts that is not useful. Also, we use several strain gauge and tiltimeters. So we combine this structural information along the day, continuously, every hour, every day. So as you can see here, maybe we can pass from the wake in motion that gives an overview about the traffic. I can put today so far, so I think it's going to be late, so we can put a different time range. This one. Exactly. Now you can see basically in the last 24 hours how the traffic changed. I can do a question for you. Basically, for some people, maybe the most important condition that we should monitor is in the 8 in the morning, where all the trucks, basically all the cars are lying on the bridge. So this could be like the maximum load that the bridge should resist. But in the other hand, having this system, basically the Rhode Island was able to understand that a lot of trucks, especially those ones that are not allowed because they are passing with more than 40, 50 tons, basically are passing with a high speed and they are impacting the joints with a much more high velocity and acceleration. So here you can understand every type of truck and cars that is passing on the bridge for every line. Basically, we assume that in one line so they are passing 2 different categories. And here you can see the trend for a lot of the lines. And I will go a little bit further. You can see also the growth-based vehicles, how it changed the speed. So someone would ask why this data are important, because basically you can do a load rating calculation, live site-specific, because we correlate this data with the structural performance on the bridge. And last but not least, we can do a very quick estimation on the WIM line load. So it gives to us an estimation of the live load for each line. And this could be calibrated for a finite element model, and we are doing also this. This is the end of my presentation, and thanks a lot for the interest.
And our last presenter for the day is Move Solutions.
Okay, just a second. No, this one. Yeah. This is standard.
Duplicate.
Duplicate. Okay. Just a second, please. Let's see if it's gonna connect it. Okay. Here it is. Come on. Okay, perfect. Perfect. Okay. Good afternoon, everyone. Let me briefly introduce myself. I'm Alessandro Nobili. I'm a civil engineer with a strong passion for structures, as many of you here today. It's truly an honor for me to be here in front of you representing my company, Move SPA, with its business unit, Move Solutions and MoveX, an Italian and American company, leader in the field of wireless structural health monitoring, both static and dynamic. The company has began its journey in 2017, and today we operate actively in more than 45 countries worldwide. with the goal of promoting structural monitoring activities aiming at detecting potential and progressive states of deterioration, ultimately contributing to the safeguarding of human life. As you can see from the video, the collapse of a portion of the remaining structure of the Beirut grain silos was actively monitored, providing a 24/7 early warning system. This was essential to ensure that all necessary operations in the surrounding port area, heavily impacted by the largest non-nuclear explosion in history, could be carried out safely and without interruption. First of all, here is an overview of the before and after to give you a clear picture of what basically is going on. Namely, the remain of a slender cylindrical structure in reinforced concrete severely damaged by the explosion of August 4th, 2020. Well, now let me walk you through the different phases of the structural monitoring that we implemented using our wireless triaxial tilt meters. How the graphs looks like. From the first monitoring campaign, which lasted an entire year, our sensor basically detected the phi and theta angles plus temperatures. And as you can find here, basically we are observing a fluctuating, predominantly planar behavior, mainly driven by seasonal temperature variation. In the second phase, on the other hand, a few sensors started recording an increase in rotations exceeding multi-level alarm thresholds. This triggered a suspension of ongoing operations and the closure of the surrounding area. In the third phase, the rotations reached significant values, over 12 degrees, corresponding to the collapse that we previously shown. By concluding this first case study, let me tell you that the system is still operating on the remaining standing up structures since 2021. Before moving on to the second case study, let me point out that Move Solutions is currently the only company in the world that can supporting both static and dynamic wireless monitoring via the LoRaWAN protocol. And let's move on. Okay. The bridge I'll show you here is the East Huntington Bridge, located in West Virginia. This 900-foot cable-stay bridge spans the Ohio River, where our monitoring system was successfully tested by the West Virginia Department of Transportation. In addition, we did our MyMove IoT platform, a suite of advanced monitoring tools is available, capable of converting raw data recorded by the sensors installed on site into valuable structural analysis using AI and machine learning algorithms. Listed are just a few of the most ones used also for the monitoring of the bridge. Focusing briefly on the installation of our wireless accelerometers, which can operate in trigger and synchronized mode, this latter being a Move Solutions patented technology via the LoRaWAN protocol, we are able to deliver highly valuable structural information with an impressively easy and fast deployment process. Here, in fact, you can clearly see how easy it was to detect the failure of a damper on one of the bridge's cable. But now let me skip on the platform so you will be able to assess and visualize by yourself the analysis that we conducted. Basically, we perform an operational model analysis, and here you can find, for example, the first model form of an approaching span of the bridge. Otherwise, just moving to another frequency, you will be able to assess another model form related to a torsional movement of the second order, for example. Considering this an SHM in action, let me skip again to another tool that is what we are looking at. This is our vibrometer that is recording data since I was starting my presentation. Thank you very much for your attention.
incredible but possible. We finished before 6. So thank you very much for attending this great show. Thanks all the presenters. It was really exciting to see, all this advancement in SHM. And
And I would also like to acknowledge the support of the support staff. I think you did an incredible job under a very stressful situation. So well done.
Okay. Yeah. So
and now we all have to run.
yeah, and the winners will be announced during the dinner.